All right, everyone, welcome back. It's Monday, and I hope we're all back in the groove from spring break at this point. And you know how we do it. I'm going to do some reviewing. We're still a little bit on the edge of quantum mechanics this, wave functions that, as we talk about multi-electron atoms. And unfortunately, you know, I try to go easy on Mondays. Last Friday, I think that's fair to say that was an easy lecture, right? That was very descriptive. Today we're going to have a lot of equations kind of coming out of our ears. And I know I told you that we were going to finish that up a while ago, but this time I'm telling the truth. This will be the last lecture with wave functions going across the board, and I'm pretty sure about that. And we're still going to be looking at wave functions and Hamiltonians. But I promise you that it's still going to be somewhat difficult, but in a different way than all of this free wave this and hydrogen atom that. It will be a little bit easier. But today is definitely going to be one of the tougher lectures, so I just want to let you know ahead of time that that's the case. Okay, so let's review. And I spent a bit of time on writing this out because as the exams tend to be a bit more descriptive because of COVID, this and that. This would be, if you get this down, then you will have really gotten most of the things that I could ever ask on an exam about the previous lecture is going to be summarized right here. And I'm going to try to be as careful as I can with summaries, because during a lecture, I think you can, as we do some expression after the next expression after the next math, you may get lost, like, what was the original point, right? And so if that happens, then it all becomes kind of worthless because, what's the point of this, right? So here's a big picture about, as we started talking about multi-electron atoms, specifically a hydrogen anion, and of course, the universe is composed of things that have, hydrogen atoms by themselves don't really exist, because if they meet another hydrogen atom, they're going to form H2. So really, even the smallest thing you could work with really doesn't exist in nature. It comes in the form of H2. So everything else, of course, is even more complicated than that, and they all have more than one electron. So from last time, we started covering how I don't want to say difficult, but how difficult it is to describe multi-electron atoms. And we'll talk a little bit about molecules in maybe 2 lectures from now. Actually, if you can understand multi-electron atoms, molecules really aren't that different. So again, we started with a hydrogen anion. And the first layer of difficulty was knowing that we have to describe the spin-up, spin-down thing. Recall that in this universe we live in, you should have heard this in high school or freshman chemistry, electrons cannot be in the same state at the same time. It's like the Pauli principle. And as a result, we have to have a way of taking into account the spin up and spin down, even though we don't really know what spin is. It's a type of angular momentum. It's the electron behaving as though it's spinning on its axis, like the Earth, night and day. It's like that, but we don't think that it is that. But it has all the characteristics of angular momentum, a different type of angular momentum than SPD and all that. It's not that. That's the electron whizzing around the nucleus. This is what it's like it's whizzing around on its axis. Actually, more like Moon and Earth, where the Moon is the electron and the Earth is the proton. That's actually a better analogy. And of course, the Moon is still rotating. Okay, so the spin part will have wave functions, but because we don't really know what's happening, they're just these impronounceable symbols. Well, actually, it's alpha, beta. And we don't have any kind of analytical e to the theta or we don't have any of that jazz for those wave functions. But they still do a lot, and you're gonna figure that out on the next homework. Okay, so there's spin wave functions that are going to be multiplied by the space wave functions. And the space wave functions are going to still be the e to the minus r's and all that stuff we did right before spring break, which was quite a bit in its own right. Now remember, I'm not going to hark on this, but remember the fact that we multiply up like here's like 2 space wave functions. we treat the electrons as having their own wave function, so they could both have 1s orbitals, just like the 1s, you know, the functions that we did the week before spring break. The problem is that those electrons can like pass through each other, and that's a problem we can't figure out how to solve. So there's a little bit of an error in our energies. The energies are always a little too high, but we're not really sure what to do about it. Mathematicians have attacked this on supercomputers, and that's great, but we won't worry about that in this class. Okay, so we multiply out the wave functions, and so we have spin wave functions, and then the last thing we have to do is we have to have this antisymmetry thing, which I explained as when you, let me use the proper terminology, it's a mouthful, but when you permute the identities of the electrons, right, so R1 turns into R2 and R2 turns into R1, and there's a theta and phi there, I'm just not writing it out because it's just, that's a lot. You have to pick up a minus sign, so when you permute the labels on the electrons, you have to pick up a minus sign, and it's like, why would you ever do that? Well, the answer is because if you have this property and you stupidly describe something that can't exist, the wave function will equal 0. And we talked about that last time. So, cool, right? And I also mentioned how, you know, it seemed to me that a sensible solution is just not to do this. But it turns out that if you ignore this antisymmetry thing, you'll get bad answers. The quantum mechanical this and that for various things that you can measure, the measurements and the calculations won't agree. But if you impart this property to the wave function and then redo your calculations, everything works out just fine. Now, as I also mentioned, the way that you get it to do this, even as weird and crazy looking as it is, it does seem to need to do it. And the way to do that, in this case, of these two electrons paired in a 1s orbital, and this would be, you might remember this term, this is called a singlet state, where the two electrons are paired in the same orbital. Those are non-magnetic. The proper word is dimagnetic. This is a non-magnetic state. And the way we do that is we play this trick with the spin wave functions. And so you see if I turn a 1 to a 2 and a 2 to a 1 in here, that I'll pick up a minus sign. So this is the total wave function. And it's a little complicated. Now remember, this part here is because I can't distinguish between electrons 1 and 2. If I just wrote one of these terms, most classes and even textbooks never tell you that you actually have to write it this way. And I would prefer to do that too, but I don't want to tell you something that's not true, even if it's a little complicated. Remember, if you leave this other term out, then it says that you can tell electron 1 versus electron 2, like they have a different color. And that's ridiculous. So we have to, unfortunately, complicate the space part of the wave function a little bit, and that's how you do it. Okay, so that's just a review. Now for today's lecture, we're going to have to cover what happens when you don't have such a simple configuration. So let me give you an example. So let's say that we start in the 1s state. So again, we have a hydrogen anion, and we're going to shine light on it. Now you know that the other electron won't go to a 2s state because you have to have a delta L of +1. So if I shine light on this, then one of the electrons, let's give it the spin down, it will get excited to a 2p state. So let's say it goes up here. Okay. So there you go. Now how do I describe this thing? And hint, it's going to be kind of different. One of the reasons it's going to be different is, could I not do this? And I'll write it out the same way. Okay, so spin up. Now, spin up, spin down. But why not spin up, right? Maybe this thing can kind of flip on its own, which, by the way, it can. Okay, so here's my point. The reason that we're going to spend a whole lecture on this is we have to figure out how to describe this and distinguish it from, you know, this is like an excited state of the hydrogen anion. It is clearly not this. It will not be described the same way. And now we also have the extra complication of this is still a singlet because I've still got up and down, But this one is different. It's got two ups. And these will not be described the same way. So that's what we're going to figure out. Now, let me cut to the chase about, I hope this is what is of interest to you, is we're going to describe magnetism. See, this is magnetic, the type of magnetism that makes electricity, that works on your refrigerator magnet. This is a magnetic state, so that is a paramagnetic state, that's the proper word. And this is a dimagnetic state, so it's non-magnetic. Remember that there's two different types of magnetism. You've learned about magnetism, like nuclear magnetism, when you were covering organic. That's where you get NMRs. Okay, that's actually really weak. The magnetism from a nucleus is very, very weak. Hydrogen has a magnetic nucleus. It's very weak. You can't do anything with it, really, other than make an NMR work. That's on the inside of the NMR. On the outside of the NMR is the actual magnet. That is, you know, the really strong magnet that like rips your heart out if you have a pacemaker. That's electronic magnetism. Electrons are very magnetic. So that's how we make magnetic devices, is by manipulating electrons. So how does this work? Now the first thing I gotta cover is, before what I'm going to do is I'm going to start writing out, right, this wave function is for this state. So that's where we're at. Now we've got to write the wave functions for these. Now before I do that, I want to have an idea of what I should be looking for. So remember how, let me review a bit. When we covered the 3D rigid rotor, the whole Hamiltonian fixed radius, blah, blah, blah. It had, in the solutions, the 17th century solutions, we had a quantum number of L, that's the total angular momentum, that distinguishes S, P, and D. And then we had M sub L, and that distinguishes Px, Py, Pz, dz squared, dx squared minus y squared, right? We talked about that. And of course the M sub L is minus L, dot, 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 0, dot, 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 plus L. Okay, and again, that's just what the 17th century mathematicians told us. Okay, but now spin, this thing that we don't know what it is, behaves just like, it behaves like angular momentum, and it also has its own version of L, which is S. And S for a single electron is 1/2 h bar, but it's 1/2. And it can have sub-values. And those, like before, go from minus S to 0 to plus S. Okay, now for a hydrogen atom, we didn't really worry too much about spin up or spin down, but the S is 1/2, technically 1/2 h bar. As I mentioned before, we often just forget the h bar. Everything has got h bar on it. Okay, that means the M sub S, if you look at this rule, has to be minus 1/2 or plus 1/2. Right, now that's beta and that's alpha. That's spin up, spin down. That's where we get that from. Okay, now the issue I have with, let's do the more interesting case of, okay, so I won't write it out quite the same way. 1s with an electron pointing up. Let's do the other one pointing up, because this is actually kind of more interesting to do first. Okay, now here's the thing. I know that you're like, oh yeah, well that spin's still 1/2, and that one's up, that one's up. I'm not going to beat your head over this, but you can't quite do that. You can't describe spin as like this spin and then that spin, as though you can kind of separate them. I mean, you kind of can, because I drew it like up and up in this case. But reality is, you have to think about the total spin. So, I can't spell total. So, angular momentums add, right? So if I'm a gyroscope and I'm holding a gyroscope and we're both spinning, you know that a physicist, if we were in physics mechanics, probably not freshman level, sounds kind of hard, the way you would describe that, right? There's one spinning and I'm spinning, it could be going the other way and that would be weird. you would need to know the total angular momentum, and that would be the thing that you would be calculating if we were like an advanced physics student, physics mechanics. That's probably like the next class that no one takes unless you're a physics major. Okay, same deal. We have to know the total angular momentum. Now, in this case, I know it sounds like, oh, we're going to have something horrible. It's not at all. It's just 1/2 plus 1/2. It's 1, right? So that part actually ends up being easy. But now here's where it gets a little bit more complicated. Notice that ms, if the total spin is 1, it's like a p state, right? So, and we know that p states have 3. There's a px and a py and a pz. Now, of course, that's for the electron like rotating about the nucleus. This is about it rotating about its axis, kind of. All right, so, but irregardless, we are going to have 3 states. -1, 0, and +1. Now, it's not going to be a px and py and pz because that's not what we're talking about, but the point is that there has to be 3 of them. I have to have 3 different states for this. And it's already looking like, well, how in God's name could I have 3 states? Because this is what I've got. All right, well, I'll show you in a second. Let me just point out one thing. This is a minor little part, but this is called all of this is called a triplet. It's called a triplet state. And that's because the number of states, the number of m sub s states is 3. So, and that's why in this guy here, this is a singlet state. The total s is 1/2 minus 1/2 of 0. So the total spin is 0, so m sub s is also 0. So there's only 1 state, 1 singlet, 1. 3 states, triplet. Right? So that's how it works. Okay, now let me get back to what am I talking about? There has to be 3 of these. What can I ever possibly mean by that? Actually, this will surprise you how easy this is. Okay, so let's do 1s, and again, because we prepared this by absorption of light, it's in a 2p state. Here's one of them. That's the one I just drew. Here's the other. See? Down, down. I could have up, up, and down, down. Right? And how would you know the difference? Oh, that bothers me. There we go. Okay. Alpha, alpha, beta, beta. Here, I'll write that down. Alpha 1, alpha 2, beta 1, beta 2. And now I need a third. And this is going to, little commas there, this is going to be a little strange. And I will try my best to explain it. Let me give you the third one, and then I'll do my best to explain it. But it works like this. Up, down, plus down, up. Okay, so that's the third triplet state. And the way that works is alpha 1, beta 2, that sounds good, plus alpha 2, beta 1. Beta 1. Why did I put a plus? What am I doing? Okay. So these are the 3 triplet states. Now, I imagine that these two, that the fact that these two are really, they're both, 1/2, 1/2, minus a half, minus a half, does not be, that's not 0. These are the same. And nature doesn't know the difference. I'm sorry, atoms. Atoms don't really know what the difference between up and down is. That's like gravity. Electrons can't feel gravity. Gravity is really a weak thing. So these are the same thing. Now this guy, I know this is a little weird, and I don't really fully understand it myself. This looks like 2 singlet states, right? Total S of 0, total S of 0. Half, half, minus half, minus half, those add up to something not 0, but this is 0 and that's 0. So why is it, if I add them up, why is that a triplet? All right, here's the best explanation I could ever give, and it's not even going to be that great, but it's the best I can do. If the length of my arm is the total spin, then here's the alpha alpha, and here's the beta beta, right? And the fact that my arm has some length is like the magnitude of the vector. And the direction, alpha alpha, beta beta. Now notice that there's clearly a third direction which is coming at you. Up, down, and coming at you, in plane. Now that would be the third direction, right? That would actually be, all right, that's alpha alpha, beta beta, and then this is the alpha beta plus beta alpha. So again, this is it fully up, both down, but then how do you describe this one? You describe it this way. So it still has, my arm is still yay long. Oh, I've been working out. My arm is still yay long, and that means that I have a spin that's not zero. It's a triplet state. But I have to have three different ones, and so this is the only way to do that, and the only mathematical way to describe that is this way. Now, again, I hope that helps, but even personally, I'm still a little confused, because this is still up, down, and that's, anyway, I can't say that I fully get it myself, but that's the best I can do. Okay, so we have three spin wave functions, triplet states. And as we're going to explore further, by the way, it turns out that this is going to be lower in energy than a singlet state. The same thing with, if that was up and down. Anyway, I'm getting ahead of myself. Before we stop talking about triplet states, let me point out something that I know that there's a whole bunch of moving parts. One of the moving parts was the antisymmetry bit, right? And remember, if I switch two electrons, right, it's right here. I don't know if you can see that in the film, but if you switch two electrons, the labels of the electrons, for weird reasons, still, I find that strange, even still. I know I have to do it, but it's strange. If I switch the labels, I have to pick up a minus sign. But I did that trick with the spin wave functions on that 1s2 state earlier. But I don't see how I'm going to do that here, right? How do I do that here? Oh, that bothers me. Plus. It's a nice looking plus. How do I do that here? It's kind of can't, right? You may be thinking, oh, alpha 1, alpha 2 minus alpha 2, alpha 1. No, that's just 0, right? Same here. All right, so there's no way to do that with the spin wave function. So guess what? It's kind of a clever trick. So what you do is you multiply these by, let me see here. It would be psi 1 or 1. Now again, I'm just using shorthand. There's really a theta 1, phi 1 here. I don't want to have to write all that out because that sucks. Okay, here's where the antisymmetry is. You put it in the space part, right? Spin part, that was antisymmetric previously. Space part, now because this part doesn't have that property, we're going to put that into the space part. The spin part can't do it, so the space part will do it. The trick of picking up the minus sign if you change the labels. And I guess there has to be a 1 over square root of 2. I guess there has to be one for here too, but whatever. Okay, so notice that the total wave function is the product of the two. And if I switch labels, this one will pick up the minus sign, which is required such that, it just is. It's required such that the electrons are always in different states, even if they're in the same orbital. And again, I've spoken about this to death, so hopefully you know what I'm talking about at this point. I don't know what to say about that. Let's see here. So the next thing I want to do is I want to show you a little bit of a trick, and then we're going to talk about magnetism. And unfortunately, the equations will go across the board quite a bit. In the case of, actually, let me also write very quickly before we move on. So that's the triplet. That's the triplet excited state. And the singlet excited state actually is going to be identical to what we did before. So let me just point out that if I had prepared this excited state such that the total spin is 0, then the wave function, the total wave function is still alpha 1 beta 2 minus alpha 2 beta 1. I'm actually writing the same thing that's below me. I just want to make sure that you know that you know what it is. It's actually not different than what I had written before. I will point out what's different. What's wrong with me? What's wrong with me? I should just speed up time, shouldn't I? Sorry, I'm writing the antisymmetry. Okay, so I'm actually writing the same thing I wrote here. So in this configuration, again, this is the excited state singlet. What's different is I still have this symmetric space part. It's just that psi 1 and psi 2 are not the same. They're not both 1s. This is a 1s, and that's like a 2pz, right? So the singlet states, the diamagnetic states, the non-magnetic states, those are actually kind of easier to understand, especially because there's only one of them. And it always looks the same. If these two orbitals are 1s orbital, that would be like the ground state of the hydrogen anion. And if that's a 1s and that's a 2pz, then it's an excited state. But either way, the whole thing is the same. The triplet is just a bit more complicated because there's three different possibilities. And then the space part is so that's 1s and that's 2pz. And last bit I'll say is, in case you're wondering, like, well, wait, how do I deal with this whole wave function? There's actually three different possible results from putting this in a triplet state. Either this is the spin state wave function, either this is the spin wave function, or this is. Now the trick here is that with lasers and polarized light and circularly polarized light and magnetic fields, you see there is a crazy amount of things that I could do to a hydrogen atom. I can prepare hydrogen atoms as spectrometers, and I can use all kinds of lasers and magnetic fields to prepare the excited state in exactly one of these. Only one of them. So I don't want you to get confused to think like this is all like one wave function. It's three different ones, and which one it is would depend on how I created the system. And again, with magnetic fields and circularly polarized lasers and all this stuff, I can create hydrogen 1s state, hydrogen anions in the 1s state, and I can selectively populate one of these three if I so choose. And then I have the wave function, and I can do quantum mechanical predictions on experiments, and then I can do the experiments, and I get the same thing, and now I feel like I know everything. So anyway, so this isn't like some strange mathematical notation. The state would be in just simply one of these three, and which one it is depends on how you made it. So again, I didn't want you to look at this like this is some kind of confusing notation, and they're all the wave function at the same time. That's not how it works. Okay, now I'm going to have to wipe out the board, and we are going to get into a little bit more complicated stuff here. We're going to now start looking at the energy of these triplet states versus the singlet states. And what I'm going to show you is that the triplet state is actually slightly lower in energy. Okay, so I'm going to wipe out the board, and then we're going to do that part next. Okay, so we're back, and I took the liberty to write out, you've already written this down, I've just rewritten it so that it will be a little bit easier to follow what I have to do next. What I have to do next is, see, I have these two wave functions, and now I'm going to evaluate their energy, because here's what happened. Again, I have my spectrometer, I have ways of creating a hydrogen anion in its ground state, where both electrons are in the 1s state. They have to be spin up, spin down. But remember that two electrons can't be in the same state at the same time. I shine light on it, and I'm probably going to get this. This is the excited state singlet because it looks like I've excited the spin down one just arbitrarily. I excited the spin down one, so I would expect it for the most part to go into the excited, and it'll go into a 2p state. If I use Z polarized light, it's in a 2pz state. And I would expect it to still stay in a spin down state. That's reasonable. However, for various reasons we're going to talk about next lecture, it could flip over, and now I've got two spin-up states. Now there's three different ways to do this, but I'm just going to do alpha-alpha to make it easy. Again, you have to pick one. It will enter a particular state, so I chose to do alpha-alpha. Okay, so there you go, and now what I need to do is calculate the energies of these two states. Now the Hamiltonian is what I wrote last time at the beginning, I think more towards the beginning of class. And let me tell you, I'm going to write all this out, and it's going to be kind of painful. Let me tell you what I can do on an exam is write all this out and ask you what the various parts are. And you've seen this del thing. I've shown you that before, and that's the kinetic energy. That's all the DDRs and DD thetas and sine theta, DD theta, blah, blah, blah. Okay, here is Coulomb's law. This is, of course, I always know that by the 4 pi e naught. That's the first electron interacting with the nucleus. Here's the second electron interacting with the nucleus. And then this is the painful part. This is the part where the two electrons are interacting with each other, which I mentioned throws a monkey wrench in our ability to solve this thing, and it's divided by the distance between the two electrons. And it's also a positive energy because it's repulsive. Remember that positive energy is actually bad, right? We like to go down in energy, not up. So this goes up. Okay. All right. Look at this. All right, now recall, I also mentioned to you that we're going to have to use the expectation value way, because if you apply these wave functions, if you just put it out here and do the operator, the problem is it's not an eigenfunction. And the reason is because of that term right there. Because it's not separatable, one of the consequences is that these are not eigenfunctions of this. It's that term that's going to mess it up. You're not going to get equal to the energy times the wave function. You're not going to see that happen. So just like when we had problems with knowing the momentum of a sine wave, remember all that free wave stuff? And I showed you that the way you get around those kinds of problems is to do expectation values. So that's what you do in this case. Because the eigenfunction way, eigenvalue equation way isn't going to work, you can do it the expectation value way, and it will work. And what you're going to, let me remind you, I just wondered, now I told you last time what it looked like. It's like 6 integrals, and let me actually simplify that, because this is, I talk about this on some of the homework, how you're going to get complex conjugate. Of course, these are the same wave function. It's not a difference dipole thing like we did in spectroscopy. And the way, in case you ever see anything like this again, when you have so many freaking integrals, r, theta, phi, oh, then you got another r, theta, and phi for the second electron. You got integral, integral, integral. The way you deal with that is to write it down a little bit more succinctly by just giving two integral signs. That means I have an electron 1, electron 2, and these little taus signify that there's an r, theta, and phi. It's just shorthand. Right? So this is how you're going to do it. And as I mentioned before, you're going to have this and this to the right, to the left, and then you're going to integrate the whole thing. There's, what did I say last time? 80 terms? Let's see. For the singlet, there's 4. 1, 2, 3, 4, 5. There's 5 terms of the Hamiltonian. 4 times 5 is 20. Times 4 more. Same thing, really, complex conjugate. 20 times 4, that's 80. And remember that when you have an integral of like a plus b, it turns into 2 integrals, right? Integral of a plus integral of b. So there's 80 integrals. Now I bet most of them are 0. Actually, they're almost all 0, but there's 80 integrals that you have to do. So that sucks. So let me not do all 80. Let's just summarize what would happen if we felt like doing that. Now remember, the people who write the software to do that, I mentioned all the supercomputers, it's an unusual group of people, but they get paid a lot. If you can do it, you're valuable, right? Okay, so of course the expectation value of the Hamiltonian is the energy by definition. And what it's going to turn into is a kinetic energy. And you know, we've done that. The way that I've done this is it'll be the kinetic energy of a hydrogen electron for the first one, plus the kinetic energy of a hydrogen electron, and that's from the second electron. So it's actually pretty understandable. It's what we had for the single electron, but there's just another electron. So this part's hopefully kind of easy to understand. Then there is the Coulombic part. And we hopefully, you know, here's the first electron in the nucleus. That's good. That's a downhill interaction, which is good. Same for the second electron. And then that one, of course, messes things up. So it seems like this would be relatively easy to understand. However, let me point out what is going to cause some really, really weird things. It's going to be these antisymmetry parts. Right? These antisymmetry parts. It's a little easier to see with the triplet. I've got all these freaking integrals, and they integrate R1 and R2 and theta 1 and theta 2 and all that, blah, blah, blah. And I've got terms. This term here is a weird one, where I've got the first orbital holding the second electron. Now that guy is going to get catfished into the integrals for, this one is going to get sucked into the integral for the second electron, and that one's going to get sucked into the integral on the first electron. So it's going to end up complicating the thing. And let me show you how it ends up being complicated. So the Coulombic part is going to end up being a little complicated. Okay. Now let me show you what that ends up looking like. Oh my God, okay. Okay, so the Coulombic part. Now that's, again, these things are kind of easy, but these things are going to create, they're going to do some things. Okay, now the first one is like this. It is going to be, okay, so it is, this first term has just the R1 in it. That means that the coordinates of the second electron are not going to do anything. You know, all this stuff gets normalized. So that term is going to just do this. And again, notice that I'm using the expectation value way of doing this calculation. And again, the integral is, there's actually three integrals, R1, theta 1, phi 1. I probably shouldn't just mention that. It's a little easier just to pretend it's not that hard. Now the second one, so of course that represents R1, theta 1, phi 1. The next term in the Hamiltonian is going to be the same thing. Oh, I guess there's a minus sign. Oh, wait a minute, what have I done? What have I done? There's a minus e squared. Sorry, that was a bit of a screw up. Okay. Anyway, the second operator, the second Coulomb operator, is the same way. And right now I'm not seeing anything weird. This is perfectly fine. Complicated, but you know, if you're just really detailed and organized, you could plug all this into those online integrators, and you could get it. Yeah, it's complicated, but it can be done. Okay, that one. That's going to cause some problems. Okay, so let's look at this. You're going to end up with two. Sorry, this is the first one, this is the second one. And let me write up the third one right here. Now, this one, because there's an R1 and an R2 in it, you're going to end up with, instead of one of these expressions, you're going to end up with two of them. because there's two different r's, right? So you're going to end up with two different expectation value type intervals. And those will look like this. Now I know that this isn't particularly obvious. You know, I'm doing like 20 steps of calculus in showing you what I end up with. So you're not going to just like look at this. You shouldn't be able to look at this and say, oh yeah, that totally makes sense. And if you do a gazillion, well, that's plus, isn't it? You know, if you want to do all the algebra, I'm sure you can figure it out. That looks weird. Okay. And then I should speed up time, shouldn't I? Okay, so that's one of them. And then here's another one. Now again, these all come from this one term. It gets split into two pieces. And that's because of the anti-symmetrized way that the wave functions are written. And remember that E squared is just a constant. Sorry, that looks bad. That bothers me. I know this is a lot to take in. Okay. So now I don't have much time left, but let me just show you. Actually, we're almost done. Okay, remember, big picture. We have this multi-electron atom. We're doing expectation value on energy. It's hideous. There's a zillion terms. Most of them are zero. It ends up being kinetic energy. Then we have the Coulomb operators. These two are just the electron 1 interacting with the nucleus, electron 2 interacting with the nucleus. But when it comes to the third term, because they're interacting with each other, the coordinates of 1 and 2 appear in the same operator. Now, because of the anti-symmetrized way that, you know, psi 2 R1, psi 2 R2, anyway, I shouldn't, anyway, the anti-symmetrized way that you write the wave function means that you don't get just like one simple expression, you end up with two. Now, double integrals, because we're integrating over, remember the operator has an R1 and an R2 in it, so you're going to be integrating over both. Now, the first term is actually perfectly sensible. Notice that this is just the probability of finding the first electron in its first orbital, right? This is the absolute value. You know, wave function times the conjugate of the wave function. First electron in its orbital. It's interacting with the Coulomb operator with the second electron in its orbital. Wave function times its complex conjugate. It's of the second electron in its orbital. This is totally sensible, just like these. These are just the two electrons interacting with each other. And they're interacting based on probably where they're at. Probably where they're at is the wave function squared, which is these parts right here, right? These parts right here. This part is perfectly sensible, as long as you understand that a wave function squared is probably where it's at. Now there's a cross term when you do all the algebra. And look at this. R1 is in its first orbital. It is in its orbital. R2 is in, the second electron is in its orbital. But on the other side of this second electron is now in the first orbital, and the first electron's in the second orbital. They've like exchanged positions. They don't really do that, but the energy expressions have a term as though they did that. And again, mind blown. I can't describe why it does this other than just derive it and show you. So this ends up being called, cleverly, an exchange integral, and it's called JEX. Now again, this guy is perfectly sensible. The two electrons are interacting with each other, it raises energy. Totally sensible. This thing is weird, 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 and I don't even really understand what it means because it's just so weird. But I know it's there. I can do the 20 pages of algebra to get here. And again, it's weird because the coordinates have changed. And again, this is happening because of the anti-symmetrized way we write the wave function. Now let me give you the end result. It ends up being positive for singlets, ends up being negative for triplets. And again, you'd have to do all the bloody horrible calculus integrals out the wazoo to see this, but that is what you get. Now what that means is that when you excite a hydrogen anion into an excited state, it seems like it would want to, you know, this is like that's 2p and this is a 1s. This is what you would think it would do, but reality is, now it probably does do this, reality is it actually lowers its energy. It lowers its energy if one of the spins flip. So it's not much, it's not a lot, but you see I've drawn this at a higher energy, and it slightly goes downhill in energy a little bit if it can go into a triplet state. And that's because of that thing I just wiped out, the exchange integral. And that's why triplets tend to be lower in energy than singlets. So I know that this is really kind of a lot to take, and I'll speak a little bit more about that next time, but let me give you a real brief synopsis of why this is important. Remember that this state is magnetic, and we like magnets. So the fact that this is lower in energy is why we can make stable magnets. Now there's another thing about this triplet state. There's one thing that's actually kind of bad about this. This is being in a triplet state. Let's say that this is actually, instead of being an H minus, let's say it's like a molecule in a triplet state. It might run into another molecule in a triplet state, and those two would react like crazy. This is like a radical, right? It's unpaired electrons, and those tend to be super reactive. So triplet states are pretty reactive, and if they run into another triplet state, it's definitely going to be reactive. Guess what's a triplet that's just like all around us? Oxygen. Oxygen is a naturally triplet molecule. Necessary as it is, but it is naturally a triplet. So let's say that this is, instead of an H minus, let's say it's DNA. And it absorbs some light, and it ends up in a triplet state. And then it runs into some oxygen, with which it will react with immediately, which it will. What have you got? Damaged DNA. Sorry, I shouldn't have said that. I should have said cancer. You now have cancer, and that's how it happens. I told you there'd be a little bit more biochem in this part. So, cancer, isn't that great? Now we got more. Anyway, so cancer runs in my family, by the way. Okay, so I've gone way over time, so I'm going to end it there. I'll review this next time, and we've got a little bit more details to polish up about these multi-electron this and that, and then we're going to get into spectroscopy, which will be kind of fun because I'll tell you about how your cell phones work, and so I will see you all, I think, on Monday. All right, I'll talk to you then.